Hello everyone. So welcome to lecture 10 on transformers, and in this lecture the topics are going to be Sumpner's test and efficiency of the transformer. So mainly we were discussing about transformer testing in the previous lecture, that is open circuit test and short circuit test, and we did some problems on it. So to continue the topic of testing of transformers, there is one another test called Sumpner's test, or it is also called Sumpner's back-to-back test, and we complete the topic, and then we'll start a new topic, that is efficiency of transformer. We have already calculated the efficiency of transformer in some of the other problems, but we'll once again have a look at what is the efficiency of the transformer and how the efficiency changes with respect to the changes in the loading level of the transformer, and so on. So with that, let's begin this topic. That is, first one I'll take up is Sumpner's test. Now, why the Sumpner test is done? What is the purpose? So the Sumpner's test is done to determine iron losses and copper losses. So this is done to iron losses and copper losses for very large transformers. So the advantage is, but one requirement is there. So that is requirement is that we need two identical transformers. So when we have two identical transformers, we can use them in one single experiment, and we can find the iron losses and copper losses for two large transformers. And the advantage is again similar to the OC test and SC test. We only supply losses from the mains, whereas machines run at full load. So if I want to run machine at full load, so I have to connect a load and then I have to run the machine at full load. But then here the trick that we are doing is there are two transformers. So one transformer will be the load on the second transformer. In turn, the second transformer will be the load on the first transformer. So both transformers are loading each other. So thereby the power is not wasted, and only power that is wasted is the losses that is sent from the supply. So let's to understand better, let's draw the circuit diagram, and then you will see how it is. So first I'll begin by taking two main supply lines. So first I'll draw a wattmeter. So you know wattmeter contains three terminals. So this is my wattmeter. So wattmeter will measure the power, and I can also have a voltmeter. So this voltmeter will measure the voltage. So basically these two are the supply lines. So here I have one phase supply, and then this line is going like this, and then this another line also is going like this. Next, what I will do I'll take two transformers. So this is first transformer. These two transformers are identical to each other. So this is the second transformer. Similarly, this is one more transformer, and this is one more transformer. And these transformers are done such that, like, let's say this is the N1 side and this is the N2 side. So this is, if I designate this as primary side and this as secondary side, I will connect such that the secondary is facing the secondary of this transformer. So that way. So this is how we have to keep the both secondaries facing each other and both primaries are facing the other side. Then you take, this is the phase and neutral. So the phase wire I am connecting to the first one, the top one, for primary of the first transformer. Similarly, the same phase wire here I am connecting to the primary of the first transformer. On the other hand, the neutral wire I will be connecting to the neutral of this transformer. Similarly, this neutral, so let me just extend it slightly. I'll connect it to the other one. So what you have seen is simply two transformers whose primaries are connected to the same supply. Now, if I don't do anything, if I leave as it is, you can always recognize like what does this wattmeter read. So if I supply full rated voltage of the primary, let's say the primary voltage here is 500 volts, and here also it is 500 volts. So if I supply full 500 volts here, then what does this wattmeter read? So of course, this wattmeter will read the iron losses of this transformer plus the iron losses of this transformer. In fact, if you simply consider only this, it is just like an open circuit test. So we can read the iron losses in this transformer. Similarly, iron losses of this transformer. So if the wattmeter reading is, let's say, 3 kilowatt, then if I divide by 2, 1500 watts is the loss in this transformer, 1500 was the iron loss in this one. So that way we can know the iron losses. So up to here, I hope you are clear with this. So let me remove the values. Now here the secondary of both is open, so there is no current flowing in the secondary winding, and the primary windings are like this. So let's mark some voltages here. Let's say this is V1, then this will be E2, induced EMF in the secondary, which will be equal to V2. Similarly, if this is V1, this will be E2. Because these two transformers are identical, it will be like this. Also notice this is the positive side, this is the negative side. This is the positive side and this is the negative side. So if such is the case, then let us say I get like this, the polarity. So what happens if I introduce a switch here, and then if I just connect this. So if this switch S is open, still there is no current. There is no current flowing in the secondary. Therefore, this wattmeter reads the iron losses. So let's call this W1. So W1 is iron losses of both transformers. Now, if I close this switch, then what happens? Will the W1 value change? So if you notice, these two are exactly equal voltages and then they are just connecting to each other. So this E2 is opposing the other E2 and this E2 is opposing the other E2. So even if I close this switch, there won't be any current flowing. So I close this switch, still the I will be equal to 0 and still the W1 will read the iron losses of both the transformers. So far so good. So these two, you have realized that these two voltages are opposing each other. Then what I'll do, let me make some place here. So these two are large capacity transformers, but I'll get another transformer which is a small capacity transformer, and then let me measure the power in this. So let me delete this. So here I have this wattmeter. So I can measure the power flowing into this winding. And I have the voltmeter. And I have another supply. So this supply will supply somewhat a smaller voltage, and let's call this wattmeter as W2, second wattmeter. Now, as I increase this supply voltage, some current starts flowing in the primary winding, and of course I have to close this switch. So because the secondary is closed, some let's say VA and let's say EA, something like that is induced here. So this induced EMF, let's say the direction is like this, plus minus. So this will be plus minus, and this will start circulating some current in this whole system. So this current I2 is only because of this voltage. The other two voltages are cancelling out each other. So these two voltages don't contribute to any current, but this EA voltage will contribute to this current. So what I'll do is I'll also introduce an ammeter here. So this ammeter will measure the current. Now I'll keep on increasing this voltage. So here let's say the variable supply. So I'll keep on increasing this voltage such that this current in here is a rated current that is flowing in the secondary. So whenever the rated current is flowing in the secondary, rated current will flow in the primary also. So this like this. So this is the path of the secondary current. Can we plot the path of the primary current also? See, here current is going downwards, right? So here the current will go upwards. Why? Because whenever current enters the positive terminal, that means this is consuming the power. So this side the power will be released. So power will go like this. So this is the arrow. So I am drawing the path of I1 current, which is again the full load. And this I1 current will go down here. Now you notice this I1 current is entering into the positive terminal. That means the power is being consumed by this transformer, and the I1 current will leave like this. And then through the negative terminal, the I1 current will keep on going. So let me just add these two. And then I1 current will come back like this, and it is consistent with this. On the other hand, since the power is entering the positive terminal, the power is being consumed here, and here you notice this I2 current is leaving the terminal, so power is being released here. So what is happening is this transformer is consuming power from the primary and giving it to the secondary, which in turn is consumed by the secondary and then given back to the primary, which in turn doing like this. So there is a circulating current setup in the primary windings and a circulating current setup in the secondary winding, and the magnitude as indicated by this ammeter will be the full load current of this both the windings on the primary and secondary side. So now the question is, where does all this power come from? Because there is a I square R loss in all these four windings. That power comes from W2. So therefore W2, so what W2 does is copper loss of both transformers. So at the same time, simultaneously, W1 is reading the iron loss of both the transformers, and W2 is reading the copper loss of both the transformers. And both these transformers that we are talking are operating at full voltage with full flux and full current. So we get more accurate results using this kind of a arrangement and setup. Now you might ask, what about the I square R loss in this transformer? What about the iron loss in this transformer, and so on? So this transformer is very low capacity transformer compared to the other two transformers. So the losses in this are negligible. The only job this is doing is just circulating the current, for which very low voltage is sufficient, because there is no resistance in this path. There is no, like, this is like a short circuit only. So it is able to do that. So with this arrangement, so this is called Sumpner's back-to-back test. So with this arrangement, so what we have is W1 reads the iron loss of both the transformers, and W2 leads the copper loss of both the transformers. And you know the efficiency is usually 3%, or like losses are only 2 to 3%. So you can run this for the entire one day for both the transformers and test it thoroughly. You can test the effect of continuous loading and temperature effects, and all these things you can test using this particular setup. So you can measure the entire throughout the day what is the power, and then through that we can do that. So we'll look at one or two example problems on this Sumpner's test. So this is something that the connections, the current flows, everything that you should have an idea. So this is what is this. Let's look at an example problem on Sumpner's test. All right. So let's look at this question. This is example 34, which is basically an example problem based on the Sumpner's back-to-back test. So you can try this test question yourself, and then try to compare your answers with my answers. So I'm working my answer now. So what do we have here? Two similar 200 kVA, two similar 200 kVA single phase transformers gave the following results when tested by Sumpner's back-to-back method. So main wattmeter W1 is 4.8 kilowatts. So you see, this is the main wattmeter W1, and this is reading 4.8 kilowatts. And we know that this wattmeter reads the iron losses of both the transformers. So 4.8 kilowatts. So therefore, I can write iron loss of each transformer is nothing but denoted by Wi, which is nothing but 4.8 by 2 which is nothing but 2.4 kilowatts. So this is the first thing. Iron loss of each transformer we have determined. Next, uh, at rated voltage, of course that is important, we need to check that. Then series circuit wattmeter W2. So what is the series circuit wattmeter? So this is the series circuit, and this wattmeter pertaining to that is W2, and this W2 is reading how much? 7 kilowatts at full load current. So full load current is flowing in both the transformers. So therefore, uh, so what is a 7 kilowatt? So what will be the full load copper loss of each transformer? Is nothing but PCU, which is nothing but 7 kilowatt by 2, which is nothing but 3.5 kilowatt for each transformer. So first transformer is 3.5 kilowatt full load copper loss and like that. So now transformer efficiency at full load 0.8 lakh PF. So under full load condition, what are the copper losses? So total losses under full load. Total losses under full load is nothing but the addition of these two, 2.4 plus 3.5, which is 5.9 kilowatts. So when the transformer is operating at full load 0.8 power factor, what will be the load on the transformer, output of the transformer? P out will be the rating of the transformer, which is 200 kVA. So each transformer is 200 kVA multiplied by power factor is 0.8. So what is the output? So 200 kVA into 0.8, 8 into 2 is 16. So 160 kilowatts is the output of the transformer. So when the transformer output is 160 kilowatt, then losses is 5.9 kilowatt. Therefore, efficiency I can find out. So this is efficiency at full load 0.8 power factor lag. So will be 160 divided by 160 plus 5.9, which is equal to, so let me use my calculator. So 160 divided by 160 plus 5.9. So I'm getting 96.44. 96.44%. So this is the efficiency of the transformer. So thus I have solved. So the A part we have solved, B part we have solved, and C part we have solved. Now coming to the D, transformer efficiency at full load 0.9 lakh power factor. So what do you think the efficiency will be? Will the efficiency increase from C to D, or will the efficiency decrease from C to D? You just think about it, and we'll now calculate it. Now what about the losses? Since the full load, both cases the transformer is operating at full load, which means transformer currents are rated currents. That is the meaning of full load, irrespective of the power factor. But then the output will change. So what is the output? So part D, this is part C. Now part D, what is the power output? 200 kVA, but this time the power output is 0.9 power factor. So therefore 180 kilowatts is the output power, 0.9 into 200. And therefore, but the losses will still be 5.9 kilowatts during the full load. So therefore, efficiency full load 0.9 power factor lag will be how much? So 180 divided by 180 plus 5.9. So let's look at it. So will this value be, so compared to this, will this value be more or less? So let's see, 180 divided by 180 plus 5.9. So I'm getting 96.826. So 96.826. So you notice that as the power factor is improved, efficiency also improves. So this is a feature of transformer that we are seeing. Of course, we'll see more detail of it in the other examples. But then here itself, you can notice when the power factor is improving, the efficiency of transformer is improving. All right. So just for the sake of it, even though it is not asked, what if power factor is 1 per unit? So in that case, the output will be nothing but 200 kilowatts, then 200 plus 5.9 kilowatt. So this will be 200 divided by 200 plus 5.9, 97.13%. So you see again there is an increase in the power factor efficiency with increase in the power factor. So anyway, that's an interesting point to note. So that we learned from this one. Now let's look at this transformer efficiency at 80% load, 0.9 lakh power factor. Now the amount of loading has reduced. So let's see. So at 80% load, what will be the at 80% load? So iron loss of course will remain constant. So what was the iron loss before? It was 2.4 kilowatts. So iron loss will still remain 2.4 kilowatts only. Whereas the copper loss will change. So right now my loading is 80%. So that is 80 by 100. I have to square this because loading is proportional to the square of the current. So 80% load means current will become 80%. Therefore, the losses will be proportional to 80 by 100 square of it. So that multiplied by the full load copper losses, which is 3.5 kilowatt. So multiplied by 3.5 kilowatt. So what is it? So let's do 80 divided by 100 to the power of 2 multiplied by 3.5. So I'm getting 2.24 kilowatts. So now what is the total losses? Total loss at 80% full load. So that will be 2.4 plus 2.24, that is 4.64 kilowatts. And what is the output? P out at 80%, 0.9 power factor. So that is also given in the question. You see, efficiency at 80% load, 0.9 lakh power factor. So in that case, what will be the output? So 200 kVA is the rating of the transformer. Power factor is 0.9 and the percentage loading is 80%, so 0.8. So this will give me the loading in kilowatts. So 200 multiplied by 0.8 multiplied by 0.9, that is 144 kilowatts. Now at 144 kilowatts output, what is the efficiency? Efficiency at 80%, 0.9 lakh. Now will this efficiency be more or less than the earlier efficiency? You can mentally think about it. So I'm just solving it now. 144 by 144 plus, what are the new losses? 4.64. Let's look at this. 144 divided by 144 plus 4.64. So I'm getting 96.878. So this is again interesting. So the interesting as compared to this efficiency. So 96.82. So full load efficiency at same power factor is 96.82. So let me just summarize all the results. So condition. So let me say loading level, power factor, and then efficiency. So loading level is 100%, full load, power factor was 0.8. Loading level is 100%, power factor was 0.9. Loading level 100%, power factor 1. And finally loading level 80%, power factor of 0.9. And what is the efficiency in all these cases? So this is what we had solved before. So last one is 96.878%. And the earlier one is 97.13%. And then even earlier one is 96.82%. And then finally the last one is 96.44%. So now you notice, compare second row and last row. The power factor is same, but by reducing the loading level, I am increasing the efficiency. So does that mean if I further reduce the loading level, instead of 80, if I say only 70%, will the efficiency be further improved? So that is one which you can try, which you can check. Similarly, if I there is there any particular level of load where the efficiency can be maximum? So all these interesting questions are coming up. Another thing, comparing first row and second row, you notice the loading level is same, but by improving the power factor, I am improving the efficiency, 96.44 to 96.82. Similarly, further improving the power factor, I am further improving the efficiency. So what is this relation between efficiency and power factor? Also, what is the relation between efficiency and loading level? So these are all interesting questions which we can tackle in further discussion in this lecture. We derive what is known as condition for maximum efficiency. So efficiency of a transformer. So in the previous problem, you had seen that efficiency of the transformer changes with the loading level, and it changes with the power factor of the load, and so on. So we'll derive at what fraction of the load is the efficiency maximum. But before even we do this, first of all, let's define what is efficiency. So efficiency is for electrical equipment generally defined as output by input. So if I input 100% of power, how much power comes out at the output? So that is what is the efficiency. So if you multiply it by 100, then you will get the percentage efficiency. Otherwise, you will get it as a fraction. Now, it is usually impractical for transformers because you can measure output, you can measure input, and you can calculate efficiency. That is because these two are almost equal to each other, because the losses in the transformer are quite less. So therefore, we first measure losses separately. You had seen Sumpner's back-to-back test, you have seen OC test, SC test. These are all different ways of measuring losses of a transformer. And then once you know the losses and you know the output, through that we'll be able to calculate the efficiency. So there are several different formulas for efficiency. So let me write it down. So you look at this first one, that's the basic output divided by input, which is also equal to output divided by output plus losses. So which is also equal to, now what is output? Output is nothing but input minus losses divided by input. So this is again equal. Now here if I once again do it, so this, divide by input both the terms, so I'll get 1 minus losses by input. So these are different ways. So 1, 2, 3, 4 different formulas for finding the efficiency. So that is fine. So now come to the condition for maximum efficiency. So what is happening is, so what are the losses? So if you look at losses of a transformer, that is nothing but iron losses plus copper losses. So where Wi is iron loss. This is fixed irrespective of what is, like whether it is a no load or half load or quarter load or 3/4 load or full load, the iron loss is always fixed because the flux is fixed. You know the working principle of the transformer. So based on that, this is fixed. And what about copper loss? So copper loss depends on level of load. So when I say half load, that means the current is half of the rated current. So therefore, but then the copper loss, what is actually copper loss? Copper loss is nothing but I1 square or not 1 or I2 square or not 2. So depending on which side you want to calculate, which data you have, you can use either of these formulas. So this I1 is fraction of the, if it is equal to full load, then it's completely full load, and that means there's no fraction. But then whatever fraction you have at half load, you will get square, so it will become 1/4. So that way the copper loss will change. So now I want to find out what is the maximum possible efficiency for the transformer. So at what level of loading? So now what is this input power? So P1 is nothing but V1 I1 cos of phi 1. So this is the input power. So now what is the losses? Losses is nothing but I1 square or not 1 plus Wi. So I have losses and I have the value for P1. So based on this, I can calculate what is the efficiency of the transformer. So how do we do that? So efficiency, so if you look at all these formulas, I'll use the last formula, 1 minus losses by input. So 1 minus losses is I1 square or not 1 plus Wi divided by input. That is V1 I1 cos of phi 1. Now if I once again write and separate it this fraction, so I1 square and then I1 it will divide. So I'll get I1 R01 at the numerator and V1 cos phi 1 in the denominator, and then plus here it will be as usual. So Wi by V1 cos phi 1 all multiplied by I1 in the denominator. So this is what I have. Now for what value of I1 is the efficiency maximum? So for that I'll differentiate this with respect to I1. So when I differentiate this, differentiation of 1 is 0, and here I1 multiplied by some value. So you know that all the other things are all coefficient of I1. So here differentiation will give me V1 cos of phi 1 plus here again this is the coefficient. So Wi by V1 cos phi 1, and then 1 by I1 differentiation will be nothing but, so minus I1 square will be in the denominator. So derivative of 1 by I1 is 1 by minus 1 by I1 square. So this minus will get multiplied with this plus, so it will become minus. So this whole of these things for the maximum condition for maxima will be this d efficiency by di1 should be equal to 0. So therefore this term should be equal to 0. So by further writing here minus R01 by V1 cos phi 1. So this term I'll take it to the other side. Then this minus will become plus again. So Wi by V1 cos phi 1 and I1 square. So now by the way, so you should be careful. This minus will apply to this plus also. So here there will be actually a minus, because this minus will apply to this term also. Then this will be again a minus. So minus into minus it will become plus, and it goes to the other side, it becomes minus again. So now if I cancel out these terms, so this term will get cancelled out, and then minus will get cancelled out, and I1 square will go to the other side. So finally I get I1 square R01 1 is equal to Wi. This is condition for maximum efficiency. So maximum efficiency will occur at that value of I1 which satisfies this condition, that is copper loss is equal to iron loss. So iron loss is anyway a fixed quantity, copper loss is a variable quantity. For a particular value of copper loss, if it matches with the iron loss, then maximum efficiency occurs at that value. So now instead of working with I1, I would like to define at what fraction of full load kVA does maximum efficiency occur. So earlier, at what value of I1 does maximum efficiency occur? That's what we try to do. Now I want to do slightly different thing. At what fraction of the full load kVA does maximum efficiency occur? So this is actually not that difficult. This is straightforward. So what we want to do is that you define x is the fraction. Let x be the fraction of I full load at which maximum efficiency occurs. So therefore x into I full load will be actually the current corresponding to maximum efficiency. But then if that is a current corresponding to maximum efficiency, then the copper loss will be this one. That should be equal to iron loss. So this condition should satisfy. Then we will get the condition for maximum efficiency. So therefore, here if I want to find out what is the value of x, so you see x square into I full load square R01 equal to Wi, and then x equal to Wi by I full load square R01 under root. So this is the fraction at which maximum efficiency occurs. So what is there in the numerator? So x is iron loss divided by full load copper loss. So if I know iron loss and full load copper loss, then based on that I can find out at what fraction will the maximum efficiency occur for the machine. Now it is possible to design the machine such that it will provide maximum efficiency for the fraction that you are wanting your transformer to operate. See, for example, I want to operate the transformer at 90%, and then therefore I am expecting 90% load. So therefore I will design the transformer such that at 90% it provides me maximum efficiency. So that way it will be useful. So let's do one or two example problems on this concept of condition for maximum efficiency of the transformer so that we understand better this. Now let's look at this formula, this problem, that is example 35, where we are interested in finding out for the transformer described in example 34, find the fraction of full load at which maximum efficiency occurs. Determine the maximum efficiency for the load power factor of 0.9 lakh. So this is the question. So let's refer to question number 20, that is example 35, which is in the previous page, that is 27 page. So this is our example that we solved before. So what we solved from this is iron losses of each transformer, copper losses at full load. This is what we want to know. So here you can see 2.4 kilowatt and 2.4 kilowatt and 3.5 kilowatt are the full load quantities. So let's first get that to our problem. So for the transformer, iron loss is 2.4 kilowatts, this is constant, and then copper loss at full load is 3.5 kilowatts. So now at what fraction does maximum efficiency occur? So just now we had derived that. This is the formula. So let's find that fraction. So x is the fraction, which is nothing but square root of Wi by Wcu at full load. So that is nothing but square root of 2.4 divided by 3.5. Since both are in kilowatts, I can cancel out that one. So let's calculate. Let me use my calculator. So SQRT 2.4 divided by 3.5. So 82.8. 828. So for this fraction, I'll get the maximum possible efficiency. So let's calculate that maximum efficiency also. So at this fraction, what is going to be the copper loss? Copper loss at this fraction will be 0.828 square multiplied by full load copper loss 3.5. And any idea what this value will be? This will be exactly 2.4 kilowatts. So that's what we are trying to do. So let's verify that. 0.828 square multiplied by 3.5. So that will give me 2.3995, which is nothing but 2.4 kilowatt. So therefore total losses will be 2.4 kilowatt plus 2.4 kilowatt. So that will be 4.8 kilowatt. Now what will be the output? So output will be kVA multiplied by power factor multiplied by our fraction x. So at that load. So what was the kVA for the transformer? So if I just once again check back. So the kVA for the transformer is 200 kVA, and the power factor we want to calculate the efficiency is 0.9 lag. So let's go back. So 200 kVA multiplied by zero point 0.9 power factor multiplied by 0.828. So this will give me the output in kilowatts. So let's do that. 200 multiplied by 0.9 multiplied by 0.828. So that will be 149.04. So 149 kilowatts, I'll just round it off. So at this output, this would be the losses. So therefore, what is my efficiency? Efficiency is output by output plus losses. So that is nothing but 149 divided by 149 plus 4.8. And this efficiency would be the maximum possible efficiency. So 149 divided by 149 plus 4.8. So 0.96879. 879 percentage. So this is the efficiency maximum. So let's verify with our earlier results. So if I verify with here, so you say, wait a minute, what about here? I am getting 0.9713. So this you are getting because the power factor was 1. So you should compare all the values where the power factor is 0.9. So let me add the one more row. So this is from example 35. So our percentage loading level was, what is the loading level we had? 82.8%. So at 82.8% with 0.9 power factor, what was the efficiency which I got? So 96.879 is the efficiency I got. So 96.879%. So this is slightly higher than this. See, for 80% loading level 0.9 power factor, this is the efficiency, but I got higher efficiency. At full load also, I could not get that much efficiency, 8.2 only, but here I got third decimal is higher. So hopefully we got this higher efficiency. So that way, at this particular loading level, this is my maximum efficiency. So even if I take this 82.7%, the efficiency will fall, or 82.9%, the efficiency will fall. So this is the where we get the maximum efficiency. So I hope you understood something from this. Let's do one more problem on this. Okay, so now we come to this interesting problem. So here, this is not like a traditional problem that we were solving. Here, we'd like to plot, make the plots comparing efficiency and loading level. So try to look at the question. You'll have to use a computer to solve this problem because you'll have to plot the solution. So the question is like this: a transformer has iron loss of 50 watts and full load copper loss of 110 watts. KVA rating is 5 and the load power factor is 0.8. So this information is given to you. Then plot the efficiency versus loading level between the range of 50 to 90%. So I can consider 50% of load. Then what is the efficiency? Then up to 90% I can consider different percentages, 51, 52, 53 and so on like that. Up at 90% again, what is the efficiency? So we know that maximum efficiency occurs at a certain fraction. So that falls between this range. So we'll try to see that pattern. Okay, so let's get starting. And then the other part is repeat the above problem with power factor of 0.9. So if I improve the power factor from 0.8 to 0.9, of course my overall efficiency also improves as we had seen before. But then let's see how it works. Okay. So for this, I don't have to use the whiteboard here or blackboard here. I'll directly go to my programming environment and I would like to program for it. So you can see this is like a typical Octave programming environment. So I would also like to teach you how to do that. So this is example 36. So transformer loading versus efficiency. So this is just a comment that I'm giving so that will be there. So I'll clear the screen and then I'll clear all the variables. So now let's define the input variables. So whenever I write this percentage, it's a comment. So it's just to make the code clear. So I want to know what is iron loss, and I want to know what is full load copper loss, which I'll denote as WC, and I want to know what is the kVA rating of the machine, and then what is the power factor of the load. So these values are given. So let's check those values. So 50 watts, 110 watts, iron and copper loss. So iron loss is 50 and copper loss is 110. And kVA rating is 5 and load power factor is 0.8 to begin with. Now given this information, I can already calculate fraction at which I'll get maximum efficiency. So let me denote it as F. So it is nothing but square root of iron losses by copper losses. If I do this, then at that fraction, I will achieve the maximum efficiency for the machine. So on the right hand side, you can see 67.42. If I load the machine up to 67.42 loading, then I'll get the maximum efficiency. But I'll choose a different range. So I'll choose the range. So let me denote X, and the range how you specify in this is starting point for the range is 0.5, and then 0.01 is the step, and then 0.9 is the ending point of the range. So this is how we define range in MATLAB or in Octave. So just for sake, I'll just remove this. So 0.5, 0.1, 0.9. That means it will be a step 0.5, 0.6, 0.7, 0.8 and 0.9. So like that. So let me show you that. So here you see on the right side 0.5, 0.6, 0.7, 0.8, 0.9. So this correspond to 50% loading, 60% loading, 70% loading, 80 and 90% loading. But then I want to do it at a more higher rate. So I'll introduce this 0.1. So then I'll get the output like this. So 74, 75, 76. Like that, at every percent, I'm calculating what is the efficiency. So this, I'll give a semicolon to suppress this one. So here I'll write choosing the range for loading. Now at different amount of loading, my copper loss will be different. So copper loss is a function of square of the loading level. So WC copper loss at X, at different loading level X, is nothing but I'll just square each element and then multiply with copper loss. So this each element of this load is squared and then multiplied with the copper loss. Then I'll get the copper loss at different values. So if I want to know what is WCX, I'll just run it here. So you can see copper loss is 27.5, 28.6, 29.7. So like that, the copper loss is varying. And at 90%, the copper loss is 89.1 watts. So this is the calculation of copper loss. Similarly, what will be the iron loss? Iron loss anyway will be same for all the values. So that is Wi is 50. So total loss at different values of X will be WCX plus Wi. So this will be my total loss. So now I have total loss. Next, copper loss, total loss I have. What will be the output? See, output I'll define as OPX. Output at fraction of load X will be nothing but kVA multiplied by X multiplied by power factor. So this is the level of output. But one thing we should be careful with the units. kVA is in kilovolts. So I'll multiply by 1000 to convert it into watts. So the output will be in watts. So now I got output and losses. So I can find out the efficiency at loading level of X. So how do I get efficiency? Nothing but output dot slash. So output is a vector. So I have to use dot slash to divide element wise division for the vector. So OPX plus loss X. So I'm dividing the output by output plus losses. So then I got the efficiency. So this is basically the calculation of copper loss, total loss, output and efficiency. So all these 4 lines four things I'm in this line number 15. I'm calculating copper loss. Line number 16 total loss. Line number 17 output, and line number 18 efficiency. Now comes the thing of plotting the results. So how do we plot the results? We use the plot command. And on the x-axis, I would like x. That is the percentage of loading. So this will vary from 50% to 90%. And on the y-axis, I would like to know what is the efficiency. So this is what I want to plot. And then I can give I want to get a star with a straight line. And I want to define some line width. So I want to define line width of 2. So this is just improving this one. I would also switch on the grid. So let's see how this, if everything is correct, so let's see how this thing will work out. So what I'm expecting, so already we had calculated that ratio F, that is, what is the value of F? 67.42 should correspond to maximum efficiency. So let us see whether that works out or not. So I'm running this code. So looks like some error is there. Oh, it is still processing. So let's just wait. So sometimes this happens. Let me check the code once again. Okay, everything looks correct. Let me check it and I'll get back to you. So we were solving this problem and I was trying to do some code. So actually there was no wrong error in the code. There was, due to some reason, the software has crashed. So I went to another resource, that is online resource. So you can see here that it is called Octave Online. So you can actually, if you don't have MATLAB or Octave installed on your system, you can actually go to this website, that is octaveonline.net. Once you go to that website, you will get an interface where you can write your code on the left side and the results will come on the right side. No need to install any software. This is done online, so you will be able to see it. So the same code which I wrote before, I just copied into this and we are able to get the solution. I'll just run it and show you. So let me quickly review the code. Line 5, iron loss is defined. Line 6, copper loss full load is defined. KVA is defined. Power factor is defined. And then I know at what fraction I'll get the maximum efficiency. Then that was somewhere around 67%. Then I'm choosing the range 0.5 to 0.9, 50%, 51%, 52%, all the way up to 90%. And in that range, I'm calculating the copper losses, total losses, output, and efficiency. We have just seen this WCX, loss X, output of X, and then efficiency at X. And finally, I'm plotting it. So only thing earlier I did was I had given the quotations for this two, and now I removed the quotations. But then it should just give a simple error, but I don't know why the entire software has crashed. But hopefully here online it will run. So I just save this code and then I'll run it. So yes, so we got this plot. So let me just scroll this aside. So now you see on the x-axis 50% to 90% is the loading level, and at different loading level I'm getting the different values of efficiency, and maximum efficiency approximately I'm getting around 67% as what it was expected. So this is the at different loading levels how the efficiency changes. This is the quite interesting thing. So the maximum efficiency does not occur at full load or at the 85% load or 80% load. It is occurring at this point. And we can actually calculate that point. I think F is the variable. So if I see the value of F 0.674, that is 67.42%, the maximum efficiency occurs. So let's go back to this paint. So what we had noticed is that for the A, plot efficiency versus loading level. So here, so on x-axis, I am saying loading level. So 50%. to 90% or zero point 0.9, and then I'm getting the something like this. So this maximum efficiency occurs at 67.42%. So that is nothing but square root of Wi by Wc, that is square root of 50 divided by 110 watts, and this is 0.6742 if you check it. Now repeat the above problem with power factor of 0.9. So with 0.9 we know that efficiency is going to increase. So what I'll do is I'll just go back. So maximum efficiency is between 96.4 and 96.45. So about 96.425 I'll write it. So efficiency maximum is 96.425%. Now let's go back here. I'll just change the power factor here 0.9, and then now if I save it and then run it again, so okay, so this time we are getting two plots. I think because hold on was there, so this I'll just say hold off. Anyway, we can even compare. So this was the earlier plot and this is the new plot. So here you see we are almost touching 96.8%. So efficiency maximum with 0.8 pf is this, and efficiency maximum with 0.9 pf is reaching 96.8%. So like this. So as the power factor improves, efficiency also improves. So this way we can use. So what I suggest you through this video is that whenever you look at a problem, don't just solve the problem for that particular parameter value. You try to use these tools like Octave, and then try to plot over a range of values, and then you will see that it is interesting. So with this, I'll end this video. So we had in this we had studied what is the condition for maximum efficiency, how the efficiency keeps on changing with the change in the load, and then we had solved some conditions and what fraction of load maximum efficiency occurs. All these things we had solved it. So I hope you learned something from this. Try it out yourself, all these things, and we'll see you in the next lecture. If you like my videos, please push the like button and you subscribe, and let the channel be known to your colleagues and your friends so that more people will benefit. Thank you.